this lesson, we are going to discuss common probability distributions that we associate with different random variables we experience under different circumstances. But we will categorize them into two. We will have discrete distributions and we'll have continuous distributions. Discrete distributions, among them, we have Bernoulli, binomial, Poisson geometric, and hypergeometric. Let's start with the Bernoulli. This is the simplest distribution in theory that you can experience. In this case, we'll consider that x can only take two values, 0 or 1. In most cases, we'll consider 1 as a success and 0 as a failure unless otherwise stated. Now, we have different cases of Bernoulli trials that we can have, but a Bernoulli trial is a random experiment in which there are only two possible outcomes. A success may say 1 and a failure 0. For instance, if you toss a coin and considering heads as successes and tails as failures, then you can only either get head success or tails as failures. Number 2, checking items from a production line where successive is an item that is not defective and failure is a defective item. We also have phoning a call center. Success is operator is free, failure no operator is free. So when you call for customer service in a service provider and you call, you have to wait, then that's a failure because the operator was not linked directly to you. Now, a Bernoulli random variable x takes the values 0 and 1 with probability that x is equals to 1 taking p and probability that x is equals to 1 minus p taking, probability x is equals to 0 taking 1 minus p, and sometimes you find q being used to represent 1 minus p. A random variable is said to be a real Bernoulli distribution if its PMF is given by probability x is equals to p raised to power x, 1 minus p raised to power 1 minus p raised to power 1 minus x for x taking value 0 and 1. And clearly we can see that this is a discrete distribution because we have two defined values that x can take. We abbreviate this by x B, P. So this means that x follows a Bernoulli random variable with parameter P because only one parameter we need to define a Bernoulli distribution. That is, P is the only parameter here. It can be easily checked that the mean and the variance of a Bernoulli random variable is mean is P, variance is P, 1 minus P. We will prove that here. Mean simply means the expected value. We are saying that this is P, but then how are we arriving at the P? We know that the random variable in question here, the Bernoulli, is being defined as P raised to power x 1 minus P raised to power 1 minus x, and x takes 0, 1, and 0 otherwise. So in this case, if we want to get expected of x, then if we want to get the expected of x, then we should get summation of our values of x, x probability of x. So this means that when x is 0, we will have 0 times probability of x. If we put x is 0 here, then we get 1 minus p. Because this becomes p raised to power 0, then 1 minus 0, so 1 minus p raised to power 1, which is itself. Then plus, we have 1 multiplied by probability when x is 1. So when x is 1, we are going to have p, then 1 minus 1, which will be 0, so we are going to have p as the probability. So as the result of multiplying 1 for x, and when we put x as 1 here, this part goes 1 minus 1, 0, so we remain with p. So if we multiply these two, we get 0, and then 1 minus p is p. So that's why we are saying that expected of x for a Bernoulli is p. The variance of x, we'll have to get expected of x squared minus mu squared. So expected of x squared, we say this means sum over all x, x probability that x is equals to x. So in our Bernoulli case, x is taking the values 0 and 1. So we are going to have summation x multiplied by probability x is equals to x is the same as x squared, rather 0 squared. Then if we put x is 0 in our equation, we've seen that we are getting 1 minus p. Then plus 1 squared, we've seen that we are getting p if we put x is 1. So this again becomes p. So if we go back to the expression for variance of x, we have expected of x squared minus mean squared or mean squared. So this will be p minus, we've got mean as p, so p squared. We can factor out p so that we have 1 minus p. Again, the expression given there is supposed to be p 1 minus p as the variance. Let's now look at a second distribution which is developed from the Bernoulli distribution. That is the binomial distribution. Actually, the binomial distribution, because we are saying that the Bernoulli distribution, it takes a success or a failure. If you repeat successive Bernoulli trials, you convert them into binomial distribution. We will use an illustration here of a case where a student is attempting questions in a multiple choice exam. Let's assume we have number 1, and in number 1, the student can answer choices A, B, C, D. Now, number 1 itself, if only one of these questions is true, assuming that A is correct, then it means that B, C, and D are wrong. And therefore, in a given question in that exam, the student has 2 options, a success or a failure. And we can be able to define P in this case. P is simply 1 out of 4, because out of these 4 choices, only one of them is correct, and therefore the probability of success P is 1 over 4. Now, assuming that we have 50 of such questions all the way to number 50, then if the student does question 1 all the way to 50, then we have developed this binomial case of 1 question into a Bernoulli with 50 trials of the same. So if you have a Bernoulli being repeated several times, it becomes a binomial distribution. And therefore, a binomial distribution is defined by 2 parameters. Actually, we say x follows a binomial with 2 parameters, p, where this is the probability of success, and this is the number of attempts or the number of trials that it is carried out. So that the distribution of a binomial p of x is equals to x is given by, if we have 2 parameters n and p, we'll have n choose x, then p raised to power x, then 1 minus p raised to power n minus x, and x takes the value 0, 1, 2, up to n, because you cannot exceed the number of trials we are having, and then 0 otherwise. This is the distribution of a binomial as given there. Of course, n choose x means n combination x, and sometimes it's written as n combination x. So this and this, they mean the same thing. And from permutations and combinations, we notice that n choose x is actually n factorial divided by x factorial n minus x factorial. So that is the n choose r we are giving there. Now, this part counts the number of outcomes that include exactly x successes and n minus x failures. In the example of the student taking an exam with 50 questions, then we are saying that we can look at, let x be a binomial with n is equals to 50, and we've seen that for any given question, for any given paper with choices A, B, C, D, the probability of getting a correct answer in a single question is 1/4. So let's look at the probability that a student will answer exactly one question correctly. That is, we are looking at probability that x is equals to 1. So that means we'll have to do n choose x, then p raised to power x, 1 minus p raised to power n minus x. So when x is 1, and we have n is 50, then we will have 50 choose 1, then p, which is, we've seen we use a quarter, then 1 minus a quarter, 50 minus 1. So this means 50 choose 1 is 50 times 1/4 times 3/4 raised to power 49. Now, this is 0.75 being raised this many number of times. So you notice that this is approximately 0. It will go to 0 because of this part of the expression. So we are saying hardly would a student attempt 50 questions, even without working them out if they were mathematical, and get 0. The chances are very low. But if you increase this to maybe what is the probability of a student getting 10 questions correct, you'll notice that this probability will move away from 0, going towards 1, such that by the time we are saying a student is getting over 40%, it will be very close to 1, maybe 0.9 or 0.92. Then we can come back here. The mean and variance of a binomial random variable are respectively given by mean NP and sigma squared n minus p. These proofs can be done by applying the binomial theorem to prove them. We can also show that it's truly the binomial random variable or the binomial PDF. PMF is truly a PMF by applying the binomial principle to the expression, because if you expand these with combinations, they appear like the binomial expansion to show that it's 1. We look at an example here. You have a biased coin is tossed 6 times. The probability of heads on any toss is 0.3. So let x denote the number of heads that come up. So if you want to get the probability that the probability of heads on any toss is 0.3. So in this case, this will be a case of a binomial distribution, because we can see 6 trials represented by the 6 tosses, and we have the probability of success, that is the probability of getting ahead, being 0.3. So we have a binomial NP. Sorry, we have x follows a binomial NP with n is equals to 6 and p is equals to 0.3. So if I want probability that x is equals to 3, I simply get 6 choose 3, then p 0.3 raised to power 3, then 1 minus 0.3 raised to power 6 minus 3, which will be 6 choose 3, 0.3 raised to power 3, and 0.7 raised to power 3. So these can be fed directly into the calculator to obtain the corresponding probability. The others can be left for exercises, so that we go to the third distribution, that is the Poisson distribution. This is named after a French mathematician, Simeon Poisson. Now, in this distribution, we normally have some rate of occurrence per given time. Maybe consider number of drops falling from an oil leak in an oil transportation system per hour. Maybe we can have 10 drops per hour. So when you have the rate of occurrence and x is a discrete, then you can choose the Poisson distribution to represent such a case. So some random events that can be considered to be following a Poisson distribution include the number of hits to your website in a day. Maybe you have 1,000 hits per day of your website per day. The number of calls that arrive in each day on your mobile phones. You can have an average, or the number of calls you've received in a week. That makes your rate parameter. The rate of job submission in a busy computer center per minute, then the number of messages arriving to a computer server in any hour. So Poisson probabilities are useful when there are a large number of independent trials. So a large number here, we consider at least n of greater than 30. Otherwise, it's reasonable to use the binomial with a small probability of success on a single trial. It can also be used when a density of items is distributed over a given area or volume. The formula for Poisson distribution, if you're using the Poisson distribution to model a certain random variable, then probability that x is equals to x is given by exponential negative lambda, lambda raised to power x all over x factorial, and x starts from 0, 1, 2, all the way to infinity. So such a distribution can tell you several cases, and we normally abbreviate such a distribution as x follows Poisson with parameter lambda. This is like the number of calls arriving at a call center per minute or per hour. Lambda is the shape parameter which indicates the average number of events in a given time interval, and the mean and the variance of this distribution are equal to, now actually, if you have the mean of a Poisson being lambda, also the mean and the variance will be equal to lambda, and of course the summation of probabilities, since it's starting from 0 to infinity, then if you sum them, you're going to get 1. We check that to make sure that x has a Poisson distribution. Then we will recall that actually if we wanted to show that this is truly a PDF, then we would use the principle that summation over all x of p of x is equals to x is equals to 1. We should show this to satisfy that this is truly a PMF. Now, to show that, we need to show that summation x starting from 0 to infinity of exponential negative lambda, lambda raised to power x all over x factorial. We should show that it is equals to 1. Now, what does this imply? If we observe keenly, we notice that exponential negative lambda is independent of x. So we can factor it out, so that we are having summation of x is equals to 0 to infinity, lambda raised to power x all over x factorial. Those two are the ones that are dependent on x. So that we have exponential negative lambda, then let's repeat this, x is equals to 0 to infinity, lambda raised to power x all over x factorial. Now this is the same as exponential negative lambda. Then if I put 0, I get 1. Plus, if I put 1, I get lambda all over 1 factorial. If I put 2, I get lambda squared all over 2 factorial. If I put 3, I get lambda cubed all over 3 factorial, and that should continue all the way to infinity. But considering Taylor series expansion from calculus, exponential of x from Taylor series expansion is the same as 1 plus x all over 1 factorial plus x squared all over 2 factorial plus 3x cubed all over 3 factorial all the way to infinity. So considering this and this, then we notice that if I have this upper part here, then I can write it as exponential lambda, so that we can show that exponential negative lambda multiplied by the whole of this now becomes the exponential of this exponential lambda, which is simply exponential of negative lambda plus lambda, which is exponential of 0, which is 1. And we have shown that the PMF of a Poisson summed over all values of x also gives you 1, which proves that it's truly a PMF, are shown there. Now, remark, look at some remark here. The major difference between Poisson and binomial distribution is that the Poisson does not have a fixed number of trials. Instead, it uses the fixed interval of time. This is very important to help us differentiate between a binomial and a Poisson. We talk of rates per unit time, per second, per hour, per minute, per day, per week. When you have rate of a time interval, then we use Poisson distribution. We can do example 1. Consider a computer system with Poisson job arrival stream at an average of 2 per minute. Determine the probability that at any 1 minute interval, there will be 0 jobs. So that means we are looking at a Poisson distribution with rate parameter lambda. The solution to that would mean that lambda should take 2 per minute, job arrival, 2 per minute. So at least we can identify it's a per unit time, and that's why this takes a Poisson, not a binomial case. And again, we don't have a definite number of trials. So it means that we will use probability of x is equals to x to be equals to exponential negative lambda raised to power x all over x factorial for x is equals to 0 minute, 1 minute, 2 minutes, and so on. And therefore, if I want to know the probability that x is exactly equals to 0 jobs, then it means that I get exponential negative 2, because lambda is 2, then 2 raised to power 0 all over 0 factorial. But 0 factorial is 0 and 2 raised to power 0 is 1. 0 factorial is 1 and 2 raised to power 0 is 1. So this is simply negative lambda, which is exponential negative 2, which can easily be obtained as a value from the calculator. And of course, this value is between 0 and 1, because exponential power negative number tends to 0 as the power increases. So if you want exactly 2 jobs, you just replace x with 2. So it will be 2 raised to power 2, 2 factorial, and so on. So the rest can be left for exercises. Then another distribution we consider in discrete cases is the geometric. Actually, a geometric distribution is a case of Bernoulli where we have several successes before a failure. Now, if a student was to take an exam and in the first attempt they fail, in the second attempt they can fail again, and in the third attempt they fail again, and maybe they are to pass in the fourth attempt. So in every attempt of that exam, we have 2 options. The student can pass or the student can fail. So if they repeat it until they pass, then we convert that into a geometric distribution. So a geometric distribution will have the sample space success. This is a student who passes in the first attempt. Then success, then failure, then success is a student who passes in the second attempt, and so on, until failure, 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 failure. Then success is a student who attempts an exam 4 times, and then they pass in the 5th attempt. This is an infinite sample space, though it is still discrete. It's a discrete case, although it goes to infinity. Like, what is the probability of a sample point, say, 4 successes, then a failure? In such a case, then, we use a geometric distribution, because you see Q here means 1 minus P, 1 minus the probability of success. So you are attempting 3 times, then you are failing. You are failing 3 times, then you are passing in the 4th attempt. We define a geometric probability as P, probability of success, then 1 minus P or Q, number of attempts before a failure. So if it's 4 attempts, that's why we are getting 3 here by doing 4 minus 1 and such. The abbreviation is GeoP, because it requires just 1 parameter. This other P here, we are saying, it also means 1 minus P. So the only parameter for this geometry is P, and to be sure everything is consistent, we should check that the probability of all the sample points add up to 1. But we know that this can also be written this way. If you sum all the way to infinity, this behaves like the PDF of the binomial distribution, and it will add up to 1 to prove that it's truly a PMOF. We recall that to infinity of a convergence of a GP, because we are saying if I have a GP, like a GP would be 1 plus 1 over 3 plus 1 over 9 plus 1 over 27 plus all the way. What we are saying, as I increase the number of times, this is the first term, the second term, the third term, the fourth term, as I go towards a very big number, you notice that the denominator grows, but the numerator remains constant. Like, I'm using powers of 3 in the denominator. By the time I'm at 3 raised to power 10, the result is almost 0. So we can say that this one converges to 0. So in case it converges and we have that r is less than 1, this, the sum, if we recall the sum of a geometric sequence, when r has this property, is a 1 minus r raised to power n 1 minus r. So if I'm taking very large n, as n tends to infinity, then it means that I'm going to have a 1 minus r raised to power a very big number divided by 1 minus r. So this is what is going to 0. Because like if you have r is 0.5 and you're raising it to a power a very big number, 0.5 to a power a very big number is 0. So that's why we are remaining that for n, as n tends to infinity, then the sum of a geometric sequence is simply the first term divided by 1 minus the common ratio. That is this expression here. The CDF for a geometric distribution is given by this. This is the CDF because we are saying that we are summing of our values of x from the smallest value of x to the, and we let then the mean of a geometric is 1 of p, which can be shown, and the variance is p or q all over p squared. So we look at an example. You're told that a sharpshooter normally hits the target 70% of the time. Find the probability that her first hit is on the second shot. Now, we have defined probability of x to be equals to p q raised to power y minus 1, or x, and y here takes 0, 1, 2, all the way to infinity. So if we want them to hit in the second shot, so p, the probability that he shoots the target is 0.7. So this will mean that probability that y, not x, is 2, it will be p, then q 2 minus 1. And we know that q is 1 minus p, so is 0.3. So we are going to have 0.7 multiplied by 0.3. So the probability that they will hit it in the second attempt is 0.21. And then you're asked to find the mean and the standard deviation of the number of shots required to realize the first hit. So that is very easy. We've said that the mean expected of x for this one is p over q, is q over p, sorry. If we get back to that, we've said the mean is 1 over p. The expected of x is 1 over p, so this will be 1 over 0.7, and then the variance is q over p squared, which is actually 0.3 divided by 0.7 squared. That would give us the mean and the variance for that case. So we have examples continuing and some exercises there. So we look at continuous distributions. The first continuous distribution we consider is the uniform or rectangular. A uniform distribution assumes that the sample space will be divided into equal parts, and the probability of picking each of those parts is the same across. So a uniform distribution will have the distribution 1 over b minus a for the interval 1 over b. So if I'm having a uniform distribution on the interval 0, 1, then the uniform distribution is assuming that that sample space 0, 1 is being divided. If you're dividing it into 10 equal parts, then each of these parts has equal probability. That is why we call it uniform, has equal probability of being selected in the sample. And we denote it with U, A, B, so that B is the upper limit and A is the lower limit. And you can see here, these will always be greater than A, so that this is always positive, so that the PDF is always positive. We can get the expected value and the variance of X by using A plus B over 2, and the variance is B minus A, B minus A all over 12 respectively. And the CDF, which you can just simply get by integrating from A to some point of the PDF. That is, we've said that if I have the PDF f of x, then it implies that the CDF is obtained by getting the integral of the PDF from the smallest value of x to some point x. So that means, because we are saying that f of x is defined by 1 over b minus a, then to get the CDF of x, then I can integrate from the smallest, which is a, up to some point, say, x. Then I have 1 over b minus a with respect to, say, t. So that this one now gives me the integral here will be t, because whole of this is a constant. So I'll have 1 over b minus a t. Then I replace limits a to x. So that if I replace the limits, I'm going to get 1 over b minus a. And if I put the upper limit x minus the lower limit of t, which is a, that's why we are getting x minus a all over b minus a. And then these can be expressed in piecewise, so that the CDF of x is 0 when x is less than a. It is x minus a all over b minus a when x is in the interval BA, and is 1 exactly when x is greater than b. We also have the exponential distribution as one of the continuous distributions. It is often concerned with the amount of time until some specific event occurs. For instance, the amount of time beginning now until an earthquake occurs. Then, values for an exponential random variable occur as follows. There are fewer large values and more small values. We are looking at an example here where we consider two groups of customers in a supermarket. Customers who buy who spend large amounts of money, and customers who spend some little amount of money, depending on the definition of little according to observation. Maybe past a certain amount of money, say 10,000, and customers who spend less than 10,000. So customers who spend less than 10,000 will tend to be more in a supermarket than customers who spend more than 10,000. So it looks at reliability, which is the amount of time a product lasts. In brief, this distribution is commonly used to model waiting times between occurrences of rare events, lifetimes of electrical and mechanical devices, say. So a random variable is said to have an exponential distribution with parameter lambda greater than 0 if the PDF is defined by an exponential distribution f of x is defined as lambda exponential negative lambda x for x greater than 0, 0 otherwise. We also notice that alternatively, f of x can be defined by 1 over lambda exponential negative x over lambda. So both of these represent the exponential distribution. It depends with the type of parameter that you're looking at. Now, we should note that for the first case of the exponential distribution, if you have the first case, then the expected of x is equals to 1 over lambda, and the variance of x is 1 over lambda squared. For the second case, you have expected of x is equals to lambda, and variance of x is equals to lambda squared. So depending on the type of distribution you are using, then you will have different types of, you'll have different expressions for the mean and the variance. We can also get the CDF of the exponential by, of course, integrating from 0 to some point x. This is the result of the CDF. Let's look at an example. Torch batteries have a lifespan T years with the PDF this. Then you determine the probability that the battery falls before 25 hours. So we are having, in the example, we are having f of x being, or f of t rather, being defined by 0.01 exponential negative 0.01 t for t greater than 0 otherwise. So in this case, then, we are saying that lambda is 0.01. And therefore, if we want to look at the probability that it falls before 25 hours, then it means that we are looking at the probability that x lies between 0 and 25, which is actually integral from 0 to 25 of f of x, which is 0.01 exponential negative 0.01 t dt. So this will be 0.01 divided by 0.01 because we divide, that is a negative value. Then we have exponential 0.01 t, put limit 0 to 25. So this will be equals to negative 1, because this cancels to 1. Then if we put 25, this is a negative, we get exponential of negative 0.25 minus exponential of 0. Of course, this will be larger than this, and this will remove the negative. This is actually exponential of 0 minus exponential of negative 0.25, which actually this is 1. So 1 minus exponential negative 0.25 gives the result. And of course, we'll exceed 120. We'll exceed the 120 hours, the same as 1 minus 0 to 120. 35 and 50 can be obtained. Then that is a set of exercises. Then another distribution, another continuous distribution is the gamma distribution. We define the gamma function first because we are going to apply it here. A gamma function is defined by integral from 0 to infinity of x alpha minus 1 exponential x dx. This is called the gamma function with parameter alpha lambda. Some theorem here. One, the gamma of alpha is the same as alpha minus 1 gamma of alpha minus 1 if alpha is greater than 0. So this works for values, positive values of alpha. Then we have another theorem. Gamma of alpha is the same as alpha minus 1 factorial for positive values of alpha, or for the positive integers. Then gamma of alpha is twice u 2 alpha minus 1 exponential negative alpha squared, and gamma over half is actually equal to the square root of pi. Now the proof to that, the first proof, we have gamma of alpha is the same as, because we've defined the gamma function here, is the same as integral from 0 to infinity of this. If we integrate this using integration by parts, then we get this and this, which we, when we replace, then we get this which comes out here, because these would go to 0. This, and then a gamma function for alpha minus 2. Look keenly, if we have alpha here, then we are putting x alpha minus 1. So if we have alpha minus 2, then means we put alpha minus 1 as the gamma function. Now for alpha is equals to 1, gamma of 1 means that we are having alpha is 1 here, so 1 minus 1 is 0, so x disappears. We just have the exponential of negative x, which is actually 1. So when alpha is 1, then the gamma function is equals to 1. Now suppose it holds that alpha is equals to k, so we have gamma of k is the same as k minus 1 factorial, and this is the one we'll be using most, and then it means that gamma of k plus 1 is actually k minus 1 factorial, which is the same as k factorial. So if you have k minus 1, k plus 1 here, then it's the same as doing k factorial. If you have k minus 1, it's the same as doing k minus 1 factorial. Then these results holds for a is equals to k, then they must also hold for a is equals to k plus 1. We are just insisting that this, if alpha is k plus 1, then you will have k factorial. Then let's now look at the gamma distribution. The gamma distribution with parameters alpha, lambda. So in this gamma distribution, we are going to use two parameters, alpha and beta. It models the time required for an event to occur, given that the event occurs randomly in a Poisson process with a mean time between events of beta. So we are looking at a Poisson that is looking at events occurring, the time required for an event to occur. For example, an insurance company observes that large commercial fire claims occur randomly in time with a mean of 0.7 years between claims. Not only in real life, the gamma distribution is also widely used in many scientific, like reliability assessment and queuing theory. It's also in queuing theory, we also apply the gamma distribution. Computer theory, computer evaluations, or biological studies. In a nutshell, this distribution is used to model total waiting time of a procedure that consists of alpha independent stages, each stage with a waiting time having a distribution of exponential. So we combine exponential and Poisson distribution to generate a gamma distribution. A random variable x has a gamma distribution if its PDF is given by beta raised to power alpha all over gamma alpha, then x raised to power alpha minus 1, then beta negative exponential negative beta x for x greater than 0. So with this, we write x follows gamma alpha beta. So we specify the two parameters defining a gamma distribution. The parameter alpha is called the shape parameter, while beta is called the scale parameter. Gamma alpha is a gamma function like we have derived above, and in a theorem, if x has a gamma distribution, then the mean and the variance are defined here, and these ones can be used, but can be found by integrating this function over the limits x starting from 0 to infinity, like we've been doing before. Now, a gamma distribution can be used to define a chi distribution in this way. If v is a positive integer, a random variable x is said to have a chi-square distribution with v degrees of freedom, and if and only if a gamma distribution random with parameters these and these. So if you have such a gamma distribution, then it behaves like a chi distribution with v degrees of freedom. And if x is chi random variable, then the mean is normally equals to the degrees of freedom, and the variance is equals to twice the degrees of freedom, because we are taking it to be having v degrees of freedom. So the mean is equals to the degrees of freedom, and the variance is equals to twice the degrees of freedom. You look at an example here. Suppose the reaction time of a randomly selected individual to a certain stimulus has a standard gamma distribution with alpha 2 seconds. Find the probability that reaction time will be between 3 and 5 seconds, and b it's greater than 4. So this is gamma 2. This first we check the gamma function, because we are told alpha is 2. So we can be able to get the gamma function gamma of 2 is equals to 1, because we said gamma of 2 means 2 minus 1 factorial, which is 1 factorial, and therefore f of x, because gamma alpha is 1, the gamma function disappears because 1 factorial is 1, then it will have this shape. So if we want it to be between 3 and 4, then we integrate from the lower limit to the upper limit of our gamma function, which will give us 0.185. Probability that it's greater than 4 is the same as getting 1 minus probability that it's less than 4. So we take 1 minus, because x is starting from 0 to 4, then we'll start from 0 to 4. We are doing 1 minus because we want to be greater than. We cannot be able to obtain for values from 4 to wherever we don't know. But since we know it starts from 0, we can start from 0 to up to 4, then do 1 minus that. And that is what we are applying here. We integrate this using integration by parts, where you treat these as a linear function and this as an exponential function to get the result as 0.915. Have another example here and some exercises for you. So if you told that suppose the survival time x in weeks of a randomly selected male mouse exposed to 240 radiations of gamma, rads of gamma radiation has a gamma with alpha 8 and beta 15, to find the expected value, then the expected value is alpha times beta, and we've seen that it follows a alpha beta. It follows a gamma with alpha 8 and beta 15, and the mean is alpha times beta, and the variance is the square, the standard deviation is the square root of variance, and the variance is alpha beta squared. So you'll get this two as the results, and the probability, you just need to integrate this distribution over the interval 60, 120. And then if you want greater than that, is the same as doing 1 minus less than 30. So you can do from 0 to 30, and then you do 1 minus that. It will give you the corresponding result. That is the end of lesson 4.
These televised lectures supplement our robust online learning going on our MKU online platform. You can view more on our televised lectures via our online platform. We are in a digital era, and Mount Kenya University knows this. The following are the steps to follow so as to complete your online application. Download the application form from the website www.mku.ac.ke. Attach copies of your academic certificates and ID. Pay the application fees via M-Pesa pay bill number 270988. Your ID is the account number. 2,000 shillings is the charge for a postgraduate. You can also deposit in the bank accounts provided on the website. Then email all the above to apply@mku.ac.ke.